Welcome back to AI Podcast. I'm Daniel, and today we're unpacking an ACL 2020 paper titled LLM Agents Making Agent Tools. In one sentence, the authors show an agent that can read a research paper's code repository and turn it into a working tool that other AI systems can call.
Hi, I'm Elena. That sounds ambitious. So we're talking about an AI that doesn't just use tools, it actually makes them?
Exactly. The system is called Toolmaker. Give it a short task description and a GitHub link from a paper with code, and it builds a software environment, writes the wrapper code, tests itself, and fixes mistakes in a loop.
All right, who's leading this work?
Lead author Georg Wölflein with senior author Jakob Nikolas Kather. The work connects TU Dresden's EKFZ for Digital Health, the University of St. Andrews, Synagon AI, and clinical partners in Heidelberg and Dresden.
Got it. What problem are they trying to solve?
Most agent systems rely on tools that people handcraft and integrate. That's slow and it doesn't scale, especially in areas like biomedicine, where you need many specialized utilities. At the same time, lots of papers now release code. Toolmaker asks whether an agent can reuse that code to build reliable tools on its own.
So the gap is between having public code and actually getting it to run cleanly, with all the dependencies and quirks handled.
Right. Earlier research often generated tiny single-file functions and avoided real operating system work. That's fine for toy tasks, but real research pipelines involve complex installs, datasets, and command line steps. Toolmaker leans into reuse rather than reinvention.
Walk me through how Toolmaker works, step by step.
2 stages. First, environment setup. It clones the repo, reads documentation, installs dependencies, and encapsulates everything in a Docker container. Inside that sandbox, it can run bash commands, read and write files, list directories, and browse local docs through a small controlled server.
So it has hands, but they're inside a safe box. That makes sense.
Second, tool implementation. The agent writes a clean Python function that exposes the repo's capability in a consistent way for LLM agents. Then it runs a closed loop. Implement a first version, run a small example, assess the result, diagnose the error, re-implement, summarize what changed, and iterate. It can even reset the container to a known checkpoint, which avoids the usual "it worked on my machine" mess.
Nice. How did they evaluate this?
They built a benchmark of 15 realistic tasks. Many are biomedical, like pathology and radiology, but there are also omics, 3D vision, imaging, tabular data, and some NLP or LLM workflows. Instead of exact match answers, they use unit tests to check structure, plausible ranges, expected files, and execution stability.
That sounds closer to how people judge real tools. Does it run? Does it produce the right kind of output? And is it stable?
Exactly. For comparison, they adapted a strong software engineering agent, OpenAI, to produce the same artifacts, a Dockerized environment and a Python tool. Prompts were kept comparable, to be fair.
And the results?
On the strict task-level metric, Toolmaker built working tools for most tasks and clearly outperformed the adapted baseline. In plain terms, it was much more reliable at getting complex environments installed and wrapped correctly.
Any interesting failure cases?
One example involved protein sequences. The single example given to the agent didn't include a special mass token, but a held-out test did. Toolmaker failed that case at first. When the example included the token, it passed. The lesson is that the specification matters. If the example doesn't show edge cases, the agent may miss them.
That's a good reminder. What about cost and efficiency?
Toolmaker usually needed a couple dozen actions per tool and kept API cost modest. It did more work than the baseline, but that extra effort paid off in success rates, especially when installs were tricky.
Did they try different models or prompt tweaks?
Yes, adding short paper summaries didn't change final accuracy much, but it sometimes reduced the number of actions. Swapping in cheaper models saved cost with some reduction in accuracy. On the baseline side, changing models didn't fix the core issue, which was the difficulty of environment setup and integration.
Okay, now be a critic. What should listeners keep in mind?
First, scale. 15 tasks is a solid start, but still small, and they were curated to be solvable. Real-world repos can be messy or poorly documented. Second, reproducibility over time. Docker helps, but public repos can change or disappear. Third, specification sensitivity. Relying on one example can hide edge cases. And finally, safety. Automating installation of powerful scientific tools requires guardrails and human oversight, especially in the life sciences.
Just to clarify, this is all software side. No wet lab automation here.
Correct. It focuses on in silico workflows. The authors explicitly separate that from real-world experimentation, which would need strict oversight.
So what's the practical takeaway?
There's a pragmatic way to scale agent capabilities by reusing high-quality research code. Toolmaker shows that with OS-level control, a clean sandbox, and a tight self-debug loop, agents can convert papers with code into dependable tools. Plus, the release benchmark gives the community a realistic yardstick for future systems.
And future directions?
Broaden the benchmark beyond curated tasks. Mine richer specifications from READMEs in test folders so examples cover edge cases. Improve planning to cut iterations, and build policy checks for sensitive domains. If this line of work connects to clinical or lab settings, it should keep humans in the loop.
Sounds balanced. Thanks for the tour, Daniel.
Thanks, Elena. That's it for today's episode of AI Podcast. The paper and code are publicly available if you'd like to dig deeper. See you next time.